whatever armulate we need to solve any problem. And also you'll have like calculus toolbox, if you may. Like these are just calculus. It's not thermodynamic, but we will use these calculus tool again and again and again, so get familiar with them. And also some of the physics, right? So for example, the reversible work is always given by negative PDV. And it's important to write down, like say this one is reversible, so it's only applicable to systems which is reversible. So that's just a quick hint in how to best prepare for this class, how to use these equations more effectively. All right. And let's get started today. First, let's use these essential equations and try to work out what is the relationship between your two heat capacities. So if you remember, these are the definition of our heat capacities, right? At constant pressure, the heat capacity Cp equals to, well, Qp over change of T at constant pressure. Now Qp here is telling you that's the heat at constant pressure. And here Cv is defined as partial derivative of du, internal energy, all over temperature at constant volume. Right, so at constant volume, your U equals to Qv. At constant pressure, your H equals to Qp. And we went over those derivations before as well. Okay, so again, what we're trying to do here is find a relationship between your heat capacities at constant pressure and at constant volume. So let's just write it out together. What we have here is Cp minus Cv. And we're just plugging these terms, partial derivative of H over T at constant pressure minus partial derivative of internal energy over T at constant volume. And in here, what we're doing is let's plug in this relationship, right? So enthalpy is by definition your internal energy plus PV. So we can write out that term here to be partial derivative of U plus PV over T at constant pressure minus your partial derivative of internal energy over T at constant volume. And we can expand this relationship. Now we know P is at constant. So we have the partial derivative of internal energy over T at constant pressure plus pressure is constant, so we can take it out from our partial derivative. dV over T at constant pressure minus du over dt, constant volume. All right. So in here, obviously we have some kind of relationship between du over dt at constant pressure and du over dt at constant volume. So one of the things we want to use, and actually I can add that to our calculus toolbox, which is the total differential equation. So we have the total differential equation of internal energy, which is a function of V and T, of give you the partial derivative of U over T at constant volume plus partial derivative of U over V at constant temperature. Right, so that's just calculus. You have internal energy is dependent on two different variables. So just write out that total derivative. So we have du equals to partial derivative of U over T, V, dt. Or in here, you can write du over dt equals to partial derivative of u over t at constant volume. And here we have dv over dt. All right, so here we're just like taking, we're just subtracting, well, not subtracting, we're just dividing dt on both ends of the equation. And in here, this one, you can also consider it to be the same. It's partial derivative of volume over T at constant pressure. And this one here, du over dt at constant pressure, you can also rewrite it as partial derivative of du over dt at constant pressure. All right, so what we end up having is a relationship of du over dt at constant pressure equals to du over dt at constant volume plus partial derivative of u over v at constant temperature, partial derivative of v over t at constant pressure. All right, so that's our partial derivative of u over t at constant pressure term, which is this term here. So plug it back to our Cp minus Cv relationship, what we end up having is this whole thing plus these two terms. A little bit running out of space, but you get the idea. That's V. Sorry. And obviously we can cancel out some of the terms, right? These two terms are effectively the same. So what we end up having is this relationship. And also these two are the same. It's also both partial derivative of V over T. So we end up having the partial derivative of U over V at constant T plus pressure times partial derivative of V over T at constant pressure. And that's a relationship between our Cp and Cv, which are our two heat capacities. So now with this in hand, obviously, if you know the state, well, the gas function, or like ideal gas, you can easily work out a specific relationship for that gas. Now, if we're considering ideal gas for this example, then what is the difference between Cp and Cv for ideal gas? This first term, the change of internal energy with respect to volume at constant temperature is 0 for ideal gases. Right? Remember, in ideal gases, your internal energy is only dependent on temperature. So this term becomes 0. We have PV equals to nRT. Let me just write it here. So this term becomes 0. And we have our pressure term. And this change of volume with respect to temperature at constant P will now becomes V equals to nRT over P. So take the partial derivative of volume over temperature at constant P, you get nR equals to P for this term. Right, and this pressure will cancel out with each other. So the difference between Cp and Cv for an ideal gas now becomes nR. Well, you have a P on the bottom, and then you have a P on the top, so yeah. All right. And obviously, you can imagine apply this kind of calculation to some other state function that now you know the relationship between P and V. Might be a van der Waals gas, might be something else. But it's not hard to apply these equations, just know what we're doing here. And also, like, what is the physical meaning from what we learn here? So obviously, we have an idea, for ideal gases or for most of the gases, your heat capacity at constant pressure is likely to be a larger number comparing to your heat capacity at constant volume. So that's one of the take-home message you can obtain from these relationships. Yes?
Why was the partial derivative of U over V equal to 0?
This one?
Yes.
This one, so first of all, for ideal gases, the internal energy is just dependent on temperature. It's only dependent on temperature. Or more specifically, for monoatomic gases, we only have 3 degrees of freedom. So basically means your gas molecule can move in, well, X, Y, and Z in 3 different directions. So your U will equals to 3 over 2 times nRT. That's just the nature of the internal energy. We didn't go into very detail about how that 3 over 2 times nRT comes from. It comes from statistical mechanics, which we are not going to cover. But it's very important to know that internal energy is only dependent on temperature for ideal gases. Now, if you think about it, your ideal gases are not like interacting with each other, right? It's just like movement. It doesn't have any internal degree of freedom. So it only matters in how many ways your particle can move. And in fact, it's 3 different ways. And that's where that 3 comes from. Yes?
Can you explain why you assumed that, like, could you scroll up a bit, please?
Sure.
For the pink thing, you assumed that, like, du dt was the same as, like, the partial derivative. I was curious why you could assume that.
So here we have the, we just have, so for this example, we're saying like, okay, we're talking about constant pressure scenario. Now, at constant pressure, these 2 terms are effectively the same.
I think his question is why that's true.
Oh,
Why is that true?
I'm not sure how I can address that. It just true. Yeah. Sorry, I don't have an explanation for that. Yeah.
Can you scroll down a bit? Where did you get the partial derivative of U over V constant T plus P term down?
This
the
one?
Yellow part?
This one?
To the left. Yeah.
This one.
Where did you get the plus P from?
Oh, this one is from here. That's a P. So these 2 terms cancel out with each other.
Oh, you just factored. Okay.
Yes. Yeah.
The equation for the monatomic 3/2 center T, there's an equation for the diatomics too.
Yes and no. So it depends on if you consider that internal vibrational degree of freedom. It might be different for diatomic gases. All right, so this is just a quick demonstration in how we're using the fundamental equations and also just calculus to solve for some relationships of your thermodynamic properties. So in this case, it's Cp and Cv. And now we're moving on to a different topic, which is called the Joule-Thomson experiment. So the purpose of this section, you'll feel like a little bit off from what we just talked about. So what we are talking about here is how chemists can actually set up experiment conditions so they can measure things that are normally hard to measure. So how to set up your experiments so that you have like, for example, constant internal energy, or for example, you have constant enthalpy. So how these experiments are set up and what are the results we can get. And at the end, we'll see how these experiments, how the result coming from these experiments help us to understand the nature of some of the gases. So let's get started with the Joule experiment. So what we have here, this is a demonstration on how the Joule experiment is being set up. You can also find this figure in your textbook. So what we have is, now imagine you have two tanks. Tank A has a gas, and tank B is just vacuum in there. Right, so what we're trying to measure here is, now we start from only A containing gas, and tank A and tank B are connected by a valve. And in B, we have vacuum. And both tanks are surrounded by adiabatic wall. So if you remember what adiabatic wall means, it means we have no heat flow between inside and outside of the tank. So the total heat flow, if we're considering A plus B as our system, equals to 0. And also our gas does no work on the surroundings. So our gas does no work on its on the wall of these tanks. So what is the setup for this experiment? Now, if we let this valve go, like, how do we understand the heat, the work, and also internal energy change in this process? So what we have here is, first of all, we know this has an adiabatic wall. So by reading the condition of this experimental setup, we can translate that condition into some kind of thermodynamic property which we can use calculus to play with. So in this case, when we're saying both tanks consist of adiabatic wall, we have Q equals to 0. So that's a connection to make between an experimental setup and also some of the equation you can put down. In the setup, we also said the system does no work on the surrounding. So W equals to 0. So note that we have the W reversible equals negative PdV. So in the process, you'll be like, my gas volume is changing in the process. Why can't we use this equation here? So if you think about the process of your gas diffuse into vacuum, this process is not a reversible process. It is an irreversible process. So this equation doesn't apply anymore. So this is one of the examples I want to show you, like, okay, you have different ways to think about it, but make sure you're using the correct equation for that specific setup. Like in this case, this one just doesn't apply because it's not a reversible process. All right, yes?
Wait, why do we know it's not a reversible?
Well, you have gas on one of the tank. You have vacuum on the other end of the tank. Will that diffusion ever go back? So that's an irreversible process, right? It's not hard. It's just like double think and see, all right, is it reversible? Okay, can we consider it as reversible? It's not. And next up, what we know is this entire system is a closed system. It's actually an isolated system as well, but it's a closed system. It has no like exchange of materials with its surroundings. So we can have our first law of thermodynamics, delta U equals to Q plus W. And in this case, both heat and work are 0. So delta U is effectively 0. Or what we say is the Joule experiment is a constant internal energy or constant U process. Yeah.
Did you also say the work is 0 because the wall isn't?
It's rigid, it's not moving. Yes and no. So when we're saying the wall is not moving, you're also thinking about using this equation that the volume is not changing. But on the other hand, we can't use that dW equals to negative PdV. But it's in the setup. We're just claiming the gas is not doing any work on the surroundings. So for the Joule experiment, which is a iso-U process, what we have is we can define the Joule coefficient, which is something we can measure by doing this experiment. All right, so this mu j, that's a coefficient that can be experimentally measured. So the power of thermodynamics is now we have this experimentally measurable coefficient, like using the Joule coefficient and also, for example, our heat capacity. We can get ideas about what is the internal energy of a specific gas. So some of the things that are hard to measure, like internal energy, or internal pressure, I'm sorry. So it's the partial derivative of the internal energy over volume at constant pressure. Now, we don't have some easy way to measure the internal energy of your tank of gas. So this internal pressure is something that you can't directly measure, but you can derive it from our Joule coefficient and also the heat capacities, right? So again, the power of thermodynamics is we give you information about things that we cannot directly measure, but we can link that property like internal pressure with some of the coefficient we can measure, and you get an understanding about what's the relationship between the internal energy and volume and temperature and etc. And let's see how that's being done. It's actually pretty straightforward. We're just using our calculus here. Now, the internal pressure is defined as the partial derivative of U over V at constant temperature. So we're using our chain rule here. So that's the same as our chain rule here. And we can write out our internal pressure as negative partial derivative of U over T at constant volume, and partial derivative of T over V at constant U. Right, so what I'm doing is just moving this one to this end, and we flip whatever on the top and bottom, and you end up having the relationship we want. Right, so what is the nature of these partial derivatives? Now we have it. Now the partial derivative of your internal energy, du, over temperature at constant volume. So what is the nature of that? That's our heat capacity, CV. And this partial derivative of T over V at constant internal energy U, that's our Joule coefficient that we just defined, Joule coefficient. So now we have a way to know what the internal pressure is for a specific gas using these two properties that can be measured experimentally. Yes?
Where do you get that the internal pressure is du over dV?
That's just how people define it.
Okay.
Yeah. I mean, the idea here is not only about internal pressure, right? So you can imagine you doing that for, like, for example, dH over dB at constant T. And we'll do that later on as well. Okay, how do we feel so far? I really hope, like, this class, at the end of this class, you don't, like, know how to plug in data, and they'll be like, yeah, that's what I learned in thermodynamics, and that's not the right way to do it. Let's try focus more in what exactly we're getting from these relationships and how thermodynamics can help you in reality, right? It's not just equations. It's what we use equations for. That's the most important thing. Okay, so that's a Joule experiment. That's a same internal energy process. And we have a different variation of the Joule experiment. So that's called the Joule-Thomson experiment. So the setup for the Joule-Thomson experiment is a little bit more complicated, only a little bit more complicated than the Joule experiment. Now what you have to imagine is now you have this system, and, well, you have two different plugs that can move without any friction or anything. And on both ends, you have different pressure. You have P1 and P2. And in this case, we manually set P2 to be smaller than P1. So you have two different plug that can move, and your initial cube or initial tank, you have volume of gas and then the P1 and also at temperature 1. Now, because your P1 is larger than P2, that gas will eventually move through this internal block to the other side. All right? And we specifically say this partition or this B here, this only allow slow and reversible throttling of the gas. So if you think about the whole process, right? So the movement of your gas from the left chamber to the right chamber, so the whole process is irreversible. But if you're looking at the work that's being done at each of the steps, because the gas can only like slowly go through that internal partition, we have reversible throttling of the gas from the left part to the right part. All right, so the whole process is irreversible, but if we're looking at the work that's being done, it is a reversible process. And we know the total system is being encompassed in this adiabatic walls. So we can get a few things by using those experimental setup. First of all, we have adiabatic wall. So we have our Q equals to 0 for the process. And on the left-hand side, the piston or that plug is doing work on the gas. So on the left-hand side, what we have equals to negative. So we start from V1, we end up to be 0, P1 dV. Now our pressure is a constant value, or P1 is a constant value. So you can write that as P1 V1. Yes? That's V1 to 0. So we start from V1, we end up at 0. And on the right-hand side, so on the left-hand side, you have the plug doing work on the gas. All right, and on the right-hand side, what we have is the gas is doing work on the right plug, P2 here. So what we have is, well, we start from 0, we end up to be V2, and we have negative PdV. And here P equals to P2. And we have a negative P2, V2 here. Yes?
Just to clarify, for the work on the left side, it's also negative P1 V1.
Well, no, because here we start from V1 to 0. So it's 0 minus V1. There's a negative on the V1 as well. I skipped one of the one here. So that's negative P1 and 0 minus V1. That's how you end up to be P1 V1. Okay? With me so far? So we can write out our total work that's being done equals to work left plus work right. And let me just move to the different page and hope everyone remembers that experimental setup. So now what we have is work equals to V1, work left plus work right. That's P1 V1 minus P2 V2. For adiabatic process, Q equals to 0. And we have our delta U equals to Q plus W equals to P1V1 minus P2V2. And our delta U, by definition, we're talking about the change of your internal energy at condition 1, and the difference between the internal energy at condition 2 and condition 1. So that's U2 minus U1. All right, and moving the term a little bit, let's put 2 with 2 and 1 with 1. What we have is P1V1 plus U1 equals to U2 plus P2V2. And obviously, we have our definition for enthalpy. So we have H1 equals to H2 for the Joule-Thomson throttling experiment. All right, so we get this delta H equals to 0 by simply looking at the condition that's being set up in this specific experiment. And the Joule-Thomson coefficient is thus defined, or mu JT, to be the change, partial derivative of temperature over pressure at constant enthalpy. Okay, now let's spend a little bit more time in what if somebody actually go in there and do the experiment, and how do we interpret it, the result coming from the Joule-Thomson experiment? So imagine some chemist plotting your temperature versus pressure for the Joule-Thomson experiment. All right, so what we're doing here is effectively you have different pressure setup and you have different temperature you measured for the process. And eventually by doing different measurements, you end up getting a curve, some random curve. I'm not exactly sure what those numbers are, but some random curve. And this curve is called a isentropic curve. And you can find this curve in your textbook, which is figure 2.8. All right, so like a smooth curve for these processes. Now, what we want is the Joule-Thomson coefficient, which is a partial derivative, or in this case, it's always at constant enthalpy. So we're just looking for the slope at every point on this curve to give us the Joule-Thomson experiment coefficient. Right, so for example, if we look at here, at the maximum, you have mu JT equals to 0. And if we look at a point that's before that mu JT equals to 0, you have that to be a positive number. So what does that positive Joule-Thomson coefficient mean? It tells you, like, for example, we start from pressure 1 and we end up in pressure 2, right? So in that throttling process, your temperature will decrease when your P2 decreases. All right? So that's what that positive slope tells you. Or what we're saying is the temperature of the gas that's being used in your Joule-Thomson throttling experiment will decrease if my P2 is smaller than P1. And if we cool that gas more like largely enough, we end up having the liquefaction of the gas. And that's one of the application of your Joule-Thomson throttling experiment for liquefaction of your gas. And similarly, you get a different relationship, right? So at some different point, you have mu Jt to be smaller than 0. So that means your gas is being warmed up. All right. So this is just a quick extension. I don't think I have this part in our annotated note. I'll probably update a new version of our annotated note later today. Okay, questions?
Is the change in pressure also decreasing when the gas is being warmed?
So let's not think about it as gas being warmed. So what we have in the setup here is we set the initial pressure and we set the final pressure, P1 and P2. So what we want to know is how well the temperature of that gas change when you have different P2. All right, so now we have P2 smaller than P1. If your Joule-Thomson coefficient is larger than 0, it means your temperature will change at the same direction as your pressure change. So for positive Joule-Thomson coefficient, what we have is P2 smaller than P1, so your T2 is also smaller than T1. Alternatively, if that Joule-Thomson coefficient is a negative number, then your pressure and temperature change in different directions, right? So when pressure P2 is smaller than P1, the temperature will increase. All right. And like what we did with the Joule coefficient, we can also use the Joule-Thomson coefficient, which is something you can measure experimentally to find relationships that you normally cannot. For example, how is your enthalpy changing with respect to pressure at constant temperature? So what we're trying to find here is a relationship between dH and pressure at constant temperature. So what we're using is effectively the same thing. We're using our calculus as our tool to use things that we can measure. Like, for example, we have our Joule-Thomson coefficient to be defined as partial derivative of T and P at constant enthalpy. And we also have our Cp here, our heat capacity, is defined to be partial derivative of H over T at constant pressure. Now I'll give you like 2 or 3 minutes, just work it yourself and see if you can find it out. And you have everything you need to have our calculus, and you have these equations to use. So try it yourself. And you should. I'm just going to start writing and work it yourself as well. All right. So this is a quick demonstration in how we use the chain rule to find out some of the relationships that you don't know how to measure, right? We don't have like a thermometer for enthalpy of a specific system, but we can find out how your enthalpy change with respect to pressure at constant T. Yes.
Going back to your figure of the curve.
Oh, I can't hear you.
Going back to the figure that you drew earlier of the curve, in the blue you wrote gas is warmed up when delta P goes down.
Yeah.
You also wrote gas cools when delta P goes down. Can you just explain that concept?
Well, you have different colors. So when we're talking about different positions there, depending on what your Joule-Thomson coefficient is, you have a different relationship, or you can predict that gas to behave differently. So when you have the Joule-Thomson coefficient to be larger than 0, what you have is your temperature will decrease when your delta pressure is decreasing, right? But at a different point, at a different set of condition, when you have the Joule-Thomson coefficient to be smaller than 0, then your gas will warm up when your delta P decreases. So I will always use different colors for different things. So pay attention to the colors as well. All right, any other questions before we move on?
Can you just scroll down?
Oh, yes, sure. Yes.
And how did you get the different Joule-Thomson coefficient?
You take different measurements. So for example, what we're doing here is just for the same gas, you take the measurement at different combination of temperature and pressure, right? And you have this isentropic curve. And by taking the measurement of that curve, you get an idea about what that derivative is. And that derivative tells you what the Joule-Thomson coefficient is.
Thank you.
Let me go back here. So I know I'm already behind by one lecture, but it's okay. We'll go slow to make sure you understand everything. And next lecture is our lecture 5. So it's going to be a very interactive type of lecture. So I'll try to have some of the handout for you, the things we will be working on. If you have your iPad, feel free to work it on yourself. Or if you printed out that blank version of the lecture note, it will be very helpful. So our next lecture, we will be working on application of whatever we just derived and whatever we defined on a specific system, which is ideal gases, right? So we'll work on lots of different example problems together in our next lecture. So have that blank note ready for you, and also, well, on iPad or on paper, right? So have that blank note ready for you. And try to develop your own essential equation sheet so you don't have to like keep going back and forth to the lecture note and find those equations to use. So work on that, and we'll work out on example problems together on our next lecture. All right, good luck.